And welcome everybody. I am so glad you're here. Before I do a live stream, I'm always thinking, I wonder if anybody's going to show up. And I am so grateful to have a chance to talk with you directly, whether you're here live with me now or watching this later. Either way is great. So what I want to do in this small section of time that we have today, in this CCNA Sunday, is I'd like to review a couple of things that we've talked about in the previous sessions with VLANs and layer 2 switching, just to make sure we're on the same sheet of music. And then we'll focus on trunking. And I have 3 objectives for trunking. They are why we need it, 2, how it works, and 3, how to both configure it and verify it. So we're going to do all of that today. And let's go back to the screen. Let me go ahead and bring this up right here. All right. So as a reminder, when people, actually, let's go back to the video. When people get on a network, a user, and they just start to use their programs and applications, they just want it to work. And oftentimes they don't even care about how it works, they just want it to work. And so as a network engineer, a network technician, and as a network designer, we need to know how it works behind the scenes. And that's going to help us in both not only building networks that are functional, but also helps us in troubleshooting big time. So let's take a look at this topology and let's do a quick review of a couple quick things. And this will be totally worth it. So let me bring up a pencil tool here. So let's imagine, and this is a little bit of a review, but I think repetition is going to be the mother of learning. Let's say that this is Bob right here. And Bob's at this computer, and he wants to go out to a website. Now, Bob is going to be using a browser. Like, that's not a secret. Everybody knows about browsers, Keith. Well, when Bob uses that browser behind the scenes, the browser is using application layer services from the TCP/IP protocol suite. So in the case of a browser going to a website, it could be HTTP. So using HTTP layer services, think of that like web services. And then also behind the scenes, before Bob's computer spits that information out on the network, it's going to add information from additional layers. So HTTP at the application layer uses a transport layer protocol. And just as a, let's talk here a moment. When we say the word protocol, it's like, oh, protocol. A protocol is simply like a set of rules, like Morse code or the English language or whatever language we might speak. It's just a set of rules. And if multiple devices use that same set of rules, they understand and can communicate with each other. So that's the benefit of having a TCP/IP protocol stack. It's a set of rules that if all the devices use those same sets of rules, they can talk to each other. So the protocol at layer 4 that is used by HTTP is a protocol called TCP. That's an acronym for Transmission Control Protocol. And as that information gets added, as this logically goes down in the mind of Bob's computer is also going to add on the source IP address and the destination IP address. That means the source IP address is like the street and then the house address of where Bob is coming from, and the destination IP address is like the street and house number where Bob wants to send this packet to. And then before Bob spits it out on the network, Bob also includes additional information, including layer 2 information, which would be the source MAC addresses and the destination MAC address. I should say source MAC address singular and destination MAC address. And so every network interface card has a burned-in 12-digit address, and Bob is going to include that before he sends the information on the network. And in the previous video, we took a look, or in one of our previous videos together, we took a look at layer 2 switching, and we identified that Bob's computer, if it doesn't know the layer 2 address of another device on the local network and it needs it, it will simply ask. And that ask is called ARP, Address Resolution Protocol, where Bob's computer says, hey, everybody in the room, everybody on the network, everybody in the VLAN, I need you to look at this request, see if it's you, if it's your IP address, and if it is, please respond with your layer 2 address so I can have it. And that's how Bob's computer learns the layer 2 address, which he's including in this message that he's about to send on the wire, and then the actual bits are being sent, boom, 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 on the network. And then the switches, based on their layer 2 addresses that they see in the frames, are going to make forwarding decisions, and if the traffic is going off the local network, then we're going to forward that frame to our default gateway, and then the default gateway makes a routing decision at layer 3. So that's a separate discussion for another day, but that's how it works. So, you know what I did? I thought to myself, that's what I call myself. I said, what can I do visually to help? I know we've looked at a protocol analyzer in a previous video, but what can we do visually to help reinforce this concept of the computer doing all these steps before it sends information on the network. And I thought, let's play with some cups. And so this morning, actually last night I went out and bought some cups, and I also bought them color coded for each of the layers to help reinforce it. And I'll keep these around if we need to for explanations and understanding. We'll also use it today. So the first thing that Bob's computer is doing is using an application layer service right there. So the browser using an application layer service like HTTP, and then as it goes down the protocol stack, it's going to need to add the layer 4 information. So that whole HTTP request, whatever's in there, gets encapsulated or put inside of the header for layer 4. And that would, in the case of HTTP, it's using a TCP layer 4 protocol. So TCP is going to add its information, including sequence numbers and acknowledgements and so forth. And then as it goes down the protocol stack, at layer 3, we're going to encapsulate all of that inside of a layer 3 header. And so that layer 3 header is the source and destination layer 3 addresses, like the street names and house numbers from a layer 3 perspective. And that gets added. So every time we add a new header, and it's like encapsulating, as they call it. We're encapsulating as we go down. We're adding more and more information. And it's getting bigger and bigger because we're adding these headers for layer 4, layer 3. And then on Ethernet networks with switches, we're going to be adding layer 2 information. So we add that as well. Wow, I'm doing a fairly decent job of lining those up here. Also, the stand today for me getting these in the camera is brought to you. If it did speak, it could say, hey, I'm the right height. Anyway, that's what I'm using for the platform. And then, eventually, at some point, we spit those bits out onto the network so that the network can actually receive those. And then, the layer 2 switches, focusing on this information, the MAC addresses, make their forwarding decision. Much more effective is going to be if you use the same colors as you did in your diagrams that we've been talking about. And I thought to myself, that's true. I'm going to go ahead and redo all the labels and put them on the right colored cups and make this work so that it can be a nice reinforcement. Because this protocol stack, the TCP/IP protocol stack, is going to come in handy when we start taking a look at trunking. So let's take a look at the problem of trunking and or the problem that could come up that can be solved by trunking. And this will be answering the question, why do we need it? And let's start with this PC right here. So this is Bob's PC. Bob is currently in VLAN 10, so this port right here is assigned to VLAN 10 as an access port. And sometimes companies get large. We may have an accounting department, human resources department, sales, finance with hundreds and hundreds of users, and we aren't going to want to put them all in the same network, but we might want to have Bob. Let's say Bob works in accounting. So he is in the VLAN 10, which we're going to use for the accounting users. And let's also imagine that we have Lois over here. Now my inside joke is, if you've watched the other videos, you know I use Bob and Lois. But let's imagine that Lois is also in the accounting group. And she also is, this port right here, is also assigned to that same VLAN, VLAN 10. But they're on different switches. Well, let's just play out a broadcast that Bob is going to do. Let's say Bob is trying to ping Lois. So Bob at his command line interface says ping. Ping is an acronym that stands for Packet Internet Groper. Nobody calls it that anymore, but originally when it came up, when the guy wrote it, that's why he called it. But ping is basically a connectivity test. It tests, can we reach from where we're at to another destination and get a response back. It's a great test for basic connectivity. So let's say Bob goes to his command line interface and types ping 10.16.0.30, which is Lois's IP address. So because they're on the same network, and if they're both in VLAN 10, they're in the same, so the network is 10.16.0.0/24. That's a layer 3 network address. We'll take a look at that in separate videos. And because Bob believes that Lois is in the same network and types in ping to that address, if Bob's computer does not yet know Lois's burned-in address on her network interface card, her MAC address, what is he going to do? And I'll offer that to the group. What do you suppose a client does if it wants to ping or reach another device on the same local network but doesn't yet know the layer 2 address of that other device? What does it do? I'll give you 3 choices. 1, it gives up, says, I'm done. I can't do it. Too hard. 2, it just broadcasts everything. All future packets going to be broadcast at layer 2 to the broadcast address, so everybody gets to see it because the switch forwards broadcast for that VLAN to all other devices in the same VLAN. Or does it send an ARP request? You might be saying, Keith, yeah, I got it. It's going to do an ARP request, ARP, Address Resolution Protocol, to verify or to make that request originally of, hey, who has the layer 2 address of 10.16.0.30 that does get broadcast and sent to every other device in the VLAN, and hopefully the device that has that IP address will respond back. So, going back to our topology, let's imagine Bob sends a broadcast. So this broadcast, because it came in on port 0/1, which is in VLAN 10, the switch says, okay, my job, because this is a layer 2 broadcast, is I need to forward this to all other ports that are in the same VLAN. So it's going to forward it to any other ports locally, and we need to get that information over here to PC3. So switch 1 is going to send that broadcast between itself from switch 1 over to switch 2, because there may be clients over here also on VLAN 10, including Lois, that needs to see that ARP request, that broadcast. So here's the trick. When that frame shows up at switch 2, this broadcast, switch 2 does not need to or shouldn't forward that broadcast to any devices that are not in VLAN 10, which means it should forward it here to this port, to Lois's PCF port 1/0, because it's in VLAN 10, but it should not forward it off of 1/1, which is in a different VLAN, that's in VLAN 20. So there needs to be some mechanism between switch 1 and switch 2 that we can use to identify that, hey, this is a broadcast, but it's for this specific VLAN. And that mechanism is called a tag. What do you mean, like a skin tag? Like you get cut off at the doctor, they take a little piece of skin, they cut off? No, I mean like a little extra label. In fact, let's use this. Let's imagine that I'm going to take off the transport layer and application layer, because with a ping request, even an ARP request, there's no payload really other than just the actual request for what is your layer 2 address. So let's imagine that this is the packet and frame and bits that are going to be sent across the network from switch 1 over to switch 2. Here's what switch 1 and switch 2 agree. They agreed beforehand using a protocol or a set of rules saying this: hey, listen, anytime you send frames back and forth, says switch 1 and switch 2 together, anytime you send frames back and forth, I want you to inject a little bit and add a little label that lets me know what VLAN this is for. So switch 1 says, you mean if I send frames your way over this link, you want me to include, in addition to what the user is sending, you want me to include a little information about what VLAN it's associated with. And the other switch says yes, and I'll do the same for you. And this is called adding an 802.1q, that's the protocol, tag. And that's how we do trunking. So check this out. Let's imagine that broadcast frame right here from Bob's PC for the ARP request is about to leave. It goes into the switch, so the switch knows this is associated with VLAN 10, but before it sends that broadcast over information right there between layer 2 and layer 3. And so what this is adding a tag, an 802.1q tag that identifies what VLAN it came from. So if this is switch 1, so switch 1 has the broadcast it needs to send over to switch 2. It says, well, before I send this, I'm going to add the tag. So it adds the tag that says this frame is for VLAN 10. It then forwards it with whatever payload was above it. It could be an ARP request, HTTP, anything else, whatever else is above it. And then it sends it over to switch 2. Switch 2 gets it and looks at this tag and says, oh, this is for VLAN 10. Thanks. I'll remember that. Reassembles it because the tag is no longer needed, because now switch 2 knows what VLAN's for, and then switch 2 can properly forward that within VLAN 10 wherever it needs to go. If it's a broadcast, it'll send it to all other ports in VLAN 10, or if it's a specific layer 2 address, it'll go ahead and forward it just to the port where that switch 2 knows that layer 2 address lives. That's it. Let's do it one more time. This time, let's use an example of PC2 that needs to send a frame over to PC4. And so what would happen is PC2 sends that frame into the switch. The switch, before it sends it over the trunk, does this. It says, okay, here's the data, and possibly transport layer and application layer data as well. Everything above it is going to stay intact. And when it says, oh, this frame belongs to VLAN 20. So it does surgery. Just dropped my IP layer. It does surgery. It adds a tag. Excuse me for a moment. All right. And then it reassembles the rest of the stack. So if there was transport layer information and application layer, we put that all back as well too. It adds the tag for VLAN 20 and it sends it. Let me bring it over. There you go. And it sends it. And that way when switch 2 receives it, it says, oh, this is for VLAN 20. And then it will continue doing forwarding based on layer 2 now that it knows it's for VLAN 20. And that's a two-way street. Both devices do it. So switch 1 will include tags. Switch 2 will include tags before they send information. And the link that we're going to configure between switch 1 and switch 2 is referred to as a trunk. Trunking in Ethernet simply means we're adding a tag to indicate what VLAN that layer 2 frame is associated, and that whole packet for that matter, that frame is associated with. That's it. Boom, boom, boom. Oh, I'm putting 2 tags there. I'm going to put it back in the right order. So let's do a VLAN 10, IP network, transport layer, application layer. Fair enough, right there. There's the whole stack right there. I'll put it up so you can see it as a reference point. All right, there we go. Ta-da! All right, so our goal in this session was to identify why we need trunking to begin with, why we need tagging. And the answer is, if we're sending frames between switches and we want to communicate what VLAN this belongs to, we're going to use tagging, and the rules for that is the standard for that today, the one that we use is 802.1q. It's just the standard for injecting a tag into the frames before we send them back and forth between switches. We talked about how it works by surgically injecting it, and the last piece I'd like to talk about is actually doing it. Let's do that. Let me put these down. I'm going to move this other way too. Fortunately, it's solid state. It won't harm that. All right, so let's take a look at configuring it and verifying it. And then if you'd like, we can do some protocol analysis just to take a look and verify that that tag exists. So let me bring up the screen. Let me clear all that. And let me bring up a lab where we can actually do this. So we're going to use this topology right here with switch 1 on the left and switch 2 on the right with these associated ports. And we don't have to use all the ports, but because I want to make sure I'm trunking on both of these between switch 1 and switch 2, we're going to do that. Also, for this demonstration, this device, switch 3, is not, there's no connectivity to switch 3. I'm just going to do trunking between switch 1 and switch 2 at this point. All right. So let's bring up this lab. And let me size that so it's nice and beautiful. And let me just verify I can get to the devices I need here. Switch 1, looks good. Switch 2, PC2, PC3, PC4. Great. Now, before we begin, it's really important, I feel, it's really important to verify that we're on the right device, the right switch, before we start configuring nilly-willy. So in our topology, I'm on switch 1, and it's going to verify the VLAN assignments. 0/1 should be in VLAN 10, 0/2 should be in VLAN 20, just to confirm I'm on the right device. So let's go ahead and do that. And to do that, we'll do a show VLAN brief. That'll do it. All right, so here on VLAN 10 has gig 0/1 assigned to it, and VLAN 20 has gig 0/2 in it. That's great. And I know I'm on the right switch. All right, it's fantastic. So to configure trunking, what we're going to do is we're going to go to those interfaces, and we're going to tell them that we want to use the protocol for trunking of 802.1q, and we're also going to tell those interfaces that we want them to be a trunk, which, you know, here's the deal. We can dynamically negotiate trunking between two switches. There's VT with dynamic negotiation of trunking. But if you know you want the trunking to happen on those ports between those switches, it's better off just to tell them. So going back to our diagram, to get the right interfaces, we're going to tell interface gig 1/2 and 00 here on switch 1 that we want them both to behave as trunk ports using 802.1q. So to facilitate that, we'll go into configuration mode. And I'm going to type in interface range. You don't have to do both interfaces at the same time, but if the commands are the same, it makes a lot of sense to do it that way. So interface range gig 0/0 and also gig 1/2 and press enter. And this just indicates here that I'm in interface range configuration mode. So any commands that we do here are going to apply to both of those switches. All right, and 0012, just want to verify I got the right ports. 00 and 12. All right, perfect. I'm comfortable I have the right ports. So the two commands we're going to do are switch port trunk encapsulation .1q. And that says we want to use the .1q standard for tagging, for adding that additional information regarding the VLANs, and press enter. And then the second command is switch port mode trunk, which says, you know, dynamic negotiation's okay, but why not just go ahead and do it? And this command does that for both the interfaces. Then I'm going to configure the other side, switch 2, with pretty much the same commands on its respective interfaces. So over on switch 2, we're going to verify the interfaces here, which is 1/3 and 3/0. Okay. Again, it's really important to get the right interfaces. So config T, interface, range, gig 3/0, comma, and gig 1/3. Confirming my interfaces, yep. And then switch port trunk encapsulation .1q. Now, a long time ago, there was a Cisco proprietary, well, there still is, but no one uses it hardly anymore. There was a proprietary tagging protocol called ISL, Inter-Switch Link. And because it's so old, the standard is 802.1q, we want to use .1q. So switch port mode trunk. All right, let's do some show commands. Let's do a show interface trunk. All right, so what this says here on switch 2 is that gig 1/3 and switch gig 3/0 both are set to on as opposed to being dynamically negotiated. The encapsulation for trunking is using 802.1q. The status is trunking, that's great. And the native VLAN by default is 1. So what exactly is a native VLAN? It's a topic for another day, but the short version is if for some reason we're sending any frames for the native VLAN, in this case VLAN 1, if both switches agree, hey, the native VLAN is VLAN 1, if they ever happen to see a frame that goes coming in, and it has no tag whatsoever, even though they have trunking established, they're going to assume it's for VLAN 1, whatever the native VLAN is. So that's the short version. There's other ramifications, but that's how it works. So the native VLAN, if there's frames that are being sent associated with that VLAN, there is no tag assigned. But everything else, by default, VLAN 10, VLAN 20, any other VLANs we have are going to receive a tag, so the receiving switch can know, hey, which VLAN does this frame belong to? Okay, let's see here. So that's switch 2. Let's take a look at switch 1. Let's do a show VLAN. Show VLAN brief is like on my mind. Let's do show interface trunk. And that looks good as well. So gig 00 and 12 are both on, trunking. And down here, it shows us that gig 00, there's no VLANs being forwarded off that interface. And the reason for that is one of our upcoming topics, and that's going to be spanning tree. So I'll save that fun discussion regarding spanning tree, which I happen to love. And it's important to understand how it works. We'll save that for another day. But the short of spanning tree protocol, or STP, is that if you have parallel paths, like we do in our lab, at layer 2, there could be a loop where a frame just goes, like a broadcast goes woo, woo, clockwise and counterclockwise forever, unless we have something that identifies parallel paths and then breaks it or drops it or stops the forwarding, and that's spanning tree. Spanning tree looks for layer 2 loops and then blocks on one or more ports so we don't have a potential layer 2 loop in our switch topology. So it's on by default on corporate switches, enterprise level switches, including these, and that's why it shows no forwarding here for that specific port. And we could verify that with some spanning tree commands, and we'll do that in a separate session. Okay, so we've got trunking set up between switch 1 and switch 2. Let's test this. So from our client PC here, if we did a ping, let me get my pen. If we did a ping request, let me get out to a cool color. There we go. So if we did a ping request from 10.16.0.10, which is in VLAN 10, to PC3 10.16.0.30, if this PC had not yet learned the layer 2 address, there would be an ARP request, which would include a broadcast. Before it went over the trunk, it would add the 802.1q tag saying, hey, this is for VLAN 10. the switch 2 would receive that, strip off the tag, and then forward it as a broadcast to only devices that are in VLAN 10. So the forwarding of traffic is based on the trunks and what traffic is being allowed. So by default, all VLANs are being allowed over the trunk. So the broadcast for VLAN 10 would be sent from switch 1 to switch 2, including that tag. And then when PC3 responds back with an ARP reply, that would also be tagged with VLAN 10, switch 2 now doing the tagging, switch 1 would say, oh, thank you, and it would continue forwarding it on its local switch. And then if we did ping requests back and forth, in fact, all the traffic for VLAN 10 would be tagged 10, 10, 10, 10, 10. Now, in contrast with that, if we had PC2 that was pinging PC4, and these are both in VLAN 20, that would also be tagged. So basically every frame that needs to go over the trunk from PC2 over to PC4, it would all be tagged with 20, 20, 20, back and forth, so that switch 1 and switch 2 would be adding and removing those tags, so the receiving switch would know, oh, this is a broadcast for VLAN 20, or this is a unicast for VLAN 20, if it's a specific layer 2 address. Either way, all that traffic for VLAN 20 as it goes over the switch, over the trunks between the switch, is going to be tagged with a VLAN ID. So I thought to myself, what could we do to really drive home this point? And besides playing with the cups earlier, those cups have got to be close. There we go. So in addition to playing with these cups earlier and labeling up, I also took a few moments to do some packet captures of all those traffic patterns I just described. ARP requests from the client PC going over to PC3, and the ARP request from PC2 going to PC4, and the ping request. And what I thought I'd do is let me bring them up and I'll show them to you. I think this would be a really good opportunity to reinforce what we're looking at. So I need to find those. They're not too far away. I know I have it open. Let me have you look at the screen and not the side of my head while I dig those up. Let's see here. Where are those? I thought I had them. Hold on a second. Let me find them real quick. It'll be totally worth it. I know I created them. Okay, here we go. So let me size this down a little bit so we can see the topology and we can see these captures. All right, here we go. So I'm going to leave the topology up while we talk about this. So this is PC1, or the client PC, when it's doing its initial ARP request to PC3. So down here we have, let me get a colored pen out as well. So down here we have the ARP request. So it's an address resolution protocol request where PC is looking for the layer 2 address of PC3. But here's what I wanted to point out. In the protocol stack here, so here's the layer 2 information. Have the source layer 2 address and the broadcast destination address for the ARP request. But here's what was added by the trunk, or by switch 1 as it sent that over. It added this 802.1q header, injected surgically. And it said, basically, this frame is associated with VLAN 10. And that way, when switch 2 received it, let me go ahead and bring this down just a little bit too. When switch 2 receives that, it says, oh, that's a broadcast associated with VLAN 10. I get it. I will properly forward that to all my other devices and access ports and other trunks that are associated with VLAN 10. So if we take a look next then at the response, here's PC3's ARP reply back to PC1. So here's the ARP message, the ARP reply, but the most important part here that I want to point out is this bad boy right here. So switch 2, before it sent it over the trunk, added the 802.1q header. So we have the Ethernet information, source and destination layer 2 addresses, but before we have the IP information, it injected the tag, once again, the 802.1q tag. So as we continue this discussion, the next thing that might happen would be the actual ping request from the client PC to PC3. And so once again, as that information is being sent over the trunk, it's going to include the tag, the 802.1q tag of 10, saying, hey, this is for VLAN 10. And the same thing happens with the reply. So here's the reply from PC3, going back to PC1, and from switch 2 this time added the tag. So all this traffic was captured here on this trunk between switch 1 and switch 2, and the tag was added for VLAN 10. So the same process would happen if PC2 was trying to reach PC4. And I happen to have that right here. So here's the ARP request. So in the ARP request, it's including the 802.1q tag of 20 because PC2 is in VLAN 20. It's on an access port in VLAN 20. So when that broadcast, that ARP request came in, and then we have the response next. So here's the response coming back from PC4 to PC2, the ARP reply. Once again, this is switch 2 now, who's adding how to verify it and also how to verify it with a protocol analyzer. I use Wireshark to capture all of this information. So let me make sure, let me check my notes. We want to talk about why we need trunking. Why do we need Ethernet trunking? So if somebody asked you that right now, say, why do we even need 802.1q trunking on Ethernet? Why do we need it? And the answer is a switch who's receiving a frame from another switch needs to know, hey, which VLAN of all the VLANs that we both have configured, which VLAN does this belong to? And if you don't have the 802.1q tagging, there's not a great mechanism for the receiving switch to know. So the reason we have it is to add information. Specifically, the switch is going to add a little 802.1q tag before it sends that frame over the network so the receiving switch knows which VLAN it belongs to. So that's why we need it. That's also how it works. It adds and removes the tags as the traffic goes back and forth over the trunk. And we also looked at how to configure it. So you go to the interface and you specify a switch port trunk encapsulation, and you specify the encapsulation you want, which most of the time is going to be .1q, representing 802.1q, the standard, and then tell it to be a trunk. Don't dynamically agree to it, just do it with the command switch port mode trunk on all of the interfaces that are going to be doing trunking. So that was it. This is what I wanted to chat with you. Now, one other piece, we're not going to configure this today in the interest of time, but one other piece I wanted to share with you is this. Let me go ahead and minimize this. Right now, we have the ability to have the same VLAN, like VLAN 10, and have it on multiple switches because of the trunking. Fantastic. But what we also need to do is provide the ability to route between the 1016 network and the 172.16 networks. And to do that, we're going to need to use a layer 3 option, something that can do forwarding based on IP packets, and that would be a router. And as a couple of options, we could use this multi-layer switch with its switched virtual interfaces. I've got a separate video on that specific topic. Or we could use what's called ROAS with an external router. That's router on a stick. And the way that works is we'd configure trunking. On switch 1, we'd say, hey, trunk on port 1/2, trunk on port 00 between you and the other switch, and also trunk here on 3/2 going out to the router. And then on the router, we create logical sub-interfaces. So on a multi-layer switch, we have logical interfaces for each of the VLANs. On the router, we would also do the same similar treatment with logical sub-interfaces, one for VLAN 10, one for VLAN 20, one for VLAN 777, and then this router could do its job of routing between the VLANs. But I wanted to point out that those two options exist, and I have existing videos already in place on how the multi-layer switch works with inter-VLAN routing. And I'm not sure what it is, but anyway, there's not a whole lot of interest in router on a stick. It's like, nah, I don't want to see it. So at some point, if you want to see that, let me know, and I can add a video on that as well. But I wanted to point out that what happens in the VLAN stays in the VLAN. Layer 2 addresses are only matter in that VLAN. So whether that VLAN is on 2 or 3 or 4 switches with trunks, the layer 2 addresses only have to be unique inside of those VLANs. If we want customers to communicate outside of their local network, they are going to use a default gateway, which equates to a router, a layer 3 device that can look at the IP addresses and make forwarding decisions based on this. So let me do this. I'm going to take a quick peek at the queue. I've covered those items that I wanted to cover in this session. Let me take a quick peek at the queue, see if there's anything critical. I realize also that a lot of you have been answering questions for other people, which is fantastic. Thank you, thank you, thank you. So let me put some music on for a moment, check the queue, and I'll come back with a few final comments.
Catch me if I fall. So done with second guessing. You seem to have it all. And loving before anything emotional too soon.
Participation in the videos and these CCNA related training. All these concepts, by the way, that we've virtually everything that I've covered so far relates to CCNA, old and new. Layer 2 switching, we're going to get into layer 3 routing and so forth. So let me take a look and share with you what's coming up. And if you haven't yet subscribed, I encourage you to do so. Hit the alert bell so you get the alerts. And if you have a friend or a couple friends that are interested in getting into IT and getting into networking, hey, yeah, they can start here. That's great. We also have, of course, I think you all know we have more training on CCNA at CBT Nuggets. We did a collaborative project between Jeremy Chara, Chuck Keith, or Network Chuck, and myself, and it's a hoot. It's a lot of fun. All right, so today we did trunking, and coming up on the 12/29, which is another Sunday, another CCNA Sunday, we're going to take a look at spanning tree protocol, still staying at layer 2. Also, many people make some, spanning tree is important. It's not too tricky, but once you understand like how it works, and there's a few commands to help verify it, it's pretty amazing. Also, I mentioned this in another stream, but there are some common fallacies that people have in their minds about how it works in the pecking order of how a spanning tree operates. So I like to straighten those out too and make sure you're 100% good on spanning tree and how it works and why it's important. So we'll cover spanning tree on the 29th, and then New Year's Day at 4 p.m. That'll give you plenty of time to sleep in and all that good stuff. I had a lot of requests for OSPF network types, and at some point in the future, I will inject and we'll have a session on the topic that we just talked about, which was router on a stick, how to configure it, how a single router, external router can do routing if we're not using a multi-layer switch. So the multi-layer switch video is already in place, and you can find that on my channel. All right, so that's it. I'm so glad you joined me today, and I'll see you in the next stream. I hope your 2020, right now it's December of 2019 if you're watching the recording of this, and hope your goals for 2020 are great. One of the biggest impacts that I've had in my 2019, all of it, was a single book, and it's called Atomic Habits. And I started reading that, and I read that book probably twice a year, just to remind myself, oh yeah, okay. And it's worth the read if you're an audible person, which you subscribe to audiobooks. That works too. But if you need a book that can help you build systems to help you get what you want, I would strongly encourage Atomic Habits. It's a fantastic read. Also, I've also got some success videos on my channel. These are just like common man success tactics that anybody can use to help overcome obstacles, to help get you what you want. They're all free. So feel free to, if you need a pep of motivation someday, check one of those out. And everything I talk about in those videos, as well as these technical videos, is from experience, how it works without any hidden agenda. So I'm grateful to have you here. Hit subscribe if you haven't already. Click on the alert bell. Have a friend or two join you for these sessions. And I'll see you, my friend, in another video. Thanks, everybody.